Good morning, my dear students. In today's class, I am going to discuss about one of the important concept, radar cross section of the target. It will depend upon the target, not in radar designer hands. It will depend upon the target. It will indicate the area of the target simply. The radar cross section is the area intercepting the amount of power which when scattered equally in all directions and produces echo at the radar equal to that from target. And it is also defined as it is the measure of target's ability to reflect the radar signals in the direction of radar receiver. And then the radar cross section is given by the radar cross section sigma equal to power reflected towards source per unit solid angle by incident power density by 4 pi, that is equal to limit r tends to infinity 4 pi r square magnitude of ER by EI square, where R is distance between radar and target, ER is reflected field strength at radar, EI is incident field strength at a target. And next we can see the radar cross section of the sphere. This waveform is the radar cross section of the sphere, and at the starting we can see at the starting we have a relay region. In the relay region, the radar cross section is small compared to the wavelength. On x-axis we can see the values, that is less than 1. That means the radar cross section is less than the wavelength. That means these related to the small particle like raindrops, small air particles like that comes under relay region. And at the other end we have an optical region. This is the optical region. On x-axis we can see the values are large. That means the radar cross section is large compared to the wavelength in the optical region. In between relay region and optical region we have a resonance region. In the resonance region the radar cross section varies in an oscillatory manner. Here we can observe the radar cross section varies in an oscillatory manner with the frequency. This is the radar cross section of the sphere, and a simple all reflecting objects having a shape of a sphere. This is about radar cross section, and next I will discuss about various losses associated within the radar system. These radar system losses categorized into two types. First one is measurable losses and second one is unmeasurable losses. In measurable losses we have plumbing loss and antenna beam shape loss and collapsing loss. In unmeasurable losses we have field degradation loss. Second one is operator loss. First we will discuss about the measurable losses. In measurable losses, first one is plumbing loss. This plumbing loss is due to loose connections between the transmitter and antenna, and due to the bendings in the transmission lines at the joints we can get the plumbing losses. Poor connections and joint losses, bendings, we can get the plumbing losses. And next one is beam shape loss. In the radar equation, we know the radar equation Rmax equal to PTG sigma AE by 4 pi whole square S minimum whole power 1 by 4. Here the antenna gain G is taken as a constant. but in practice the antenna beam shape is not a constant. That means the returned echo pulses are amplitude modulated by the beam shape. That means we can have a amplitude modulated echo pulses. The targets at the center will have a high signal to noise ratio. The targets on the other side will have a small signal to noise ratio. By observing the diagram, the targets at the center of the beam shape will get the more gain. That means they will get more signal to noise ratio, and targets at the other than the center will have a small gain. That means the signal to noise ratio for that echoes is also small. It will create a beam shape losses. This is about the beam shape loss. And the next one is collapsing loss. When noise samples are integrated with the signal to noise pulses, when noise pulses are integrated with the signal to noise pulses, these noise pulses will degrade the performance. That is called a plumbing loss. That is about measurable losses. In measurable losses we discussed about plumbing losses and beam shape loss and collapsing loss. And the second one is unmeasurable losses. In unmeasurable loss, first one is field degradation loss. In field degradation loss, normally the radar system and all equipment work well in a laboratory conditions, but in field conditions the performance of the radar system will decrease. That is called a field degradation. An unexperienced person is used at for the radar maintenance, it will also create a field degradation. That is about the field degradation. And next loss is operator loss. If the experienced operator is there, then probability of detection also high. If the tired and overloaded and less experienced and not well trained operator is there, it will cause a less probability of detection. This is called a operator loss. We discussed about the various radar system losses. First one is measurable losses, second one is unmeasurable losses. In measurable losses, plumbing loss and beam shape loss and collapsing loss is there. In unmeasurable losses we have field degradation loss and operator loss is there. This is about the various radar system losses, and thank you very much.